I'm keeping track of everything. Here is my success rate so far. There are still 2 Senate races to be determined. Both are in Georgia, and both are actually what they call runoff elections. We're not going to learn about runoff elections. The only way you learn about instant runoff elections is if you took my class in discrete math, which is an elective class. But those elections in Georgia seemingly are going to go Republican, so it's going to be 52-48. Then in the House, I've already projected the House. Hold on. I've already projected the House based on all of the remaining races. Here, somebody asked me one time, like, Mr. Murray, like, do you get like paid to do this? I'm like, no, just do it for fun. Come on, kidding me? But I've projected all of the remaining. This is what I've projected the Electoral College to end up being, which I'm going to show you something in a minute. Yeah, it's still close. I mean, that's a really far number. No, that's actually pretty.
That's supposed to be the actual result.
Oh, no. But time out. This particular box was done after the election.
Oh, okay.
I'll show you the one that I did before the election.
Yeah.
Give me a minute.
Kind of
This is the projection for the Senate. Now, I had predicted a 50-50 tie. Just saying, I had predicted 50-50 tie. This is the projection for the House. Now, the funny thing about this is that, and for the Senate actually, is that the Democrats believed that they were going to run away with the House. They were going to go like up 250 with the House. And they thought that they were going to get like 54 in the Senate. But the polling was off. Did you know that in a lot of these states, Michigan, Wisconsin, North Carolina, Florida, there were tens of thousands of ballots filled out? No, I am not a fan of saying it's fake news. I'm not a fan of saying it's a fraudulent election. I'm not going to say that whatsoever. I'm of the opinion that it's on the level. So spare me. Anyway, but there's hundreds of thousands of ballots where people checked Biden and then checked Republican the rest of the way down. That's very interesting to me. The opinions of Americans are very interesting to me. I wonder why we couldn't get the opinions of Americans before the election. I don't know. Polling is off. It's not that the polls are wrong. It's the way they collect the data. The way they collect the data is broken. Literally, I've been saying that, since the middle of September, the end of September? Yes, I'm right. All right, let me show you my actual predictions. My actual predictions for the presidency. Now, this was my right here. This was my official prediction right here. But where is it? There it is. Come on, you. This was my adjusted prediction. What I have highlighted right there was my adjusted prediction. I had basically taken what I believed was going to happen to the polls, and I applied that adjustment. To the current polls, and you can see my adjustments here. So this was my prediction. So that's actually pretty darn accurate, considering this is what they assumed what was going to happen. This is what I predicted what would happen, and it was pretty darn close to that. I'm just, not to, okay, shut up, me. But I don't know, it's really interesting. I love numbers. It's so much fun. I can't wait for 2022 midterm elections. Nobody cares about midterm elections. I do. Just a lot of fun. But yeah, that's where we're at right here. Check this out. Coolest thing in the world. There's a race in Iowa, in Iowa's 2nd district, where only 89% of the vote was reporting. And here's the difference. That's amazing. That is amazing. Same thing in California's 25th. That's the difference. Well, you can see how many total votes were there. Total votes. Now, mind you, it's only 99%. Total votes versus the difference. Total votes versus the difference. So, but I have now. Basically, this was my prediction for each of those districts, and this is who is in the lead in the moment, and this is whether I was correct or I was wrong. These have not been counted into my final tabulations just yet, but based on who is in the lead, this is where I predict it'll be. You only need 218 to have the lead in the House. Now, if it ends up being 50-50, which I don't believe it will, I believe it'll be 52-48, but if it ends up being 50-50, how do they cast the tie-breaking vote in the Senate? You know, the vice president, exactly. But like I said, there's 2 races left to go. Both are in Georgia. Both are runoff elections. They're going to be recasted in January, which means people will have to go back and vote in January. So there's a lot of different reasons why people believe, yeah, the Republicans are going to win those 2 races in Georgia. But anyway. But like I said, I'm not here to talk about recounts. I'm not here to talk about fraudulent voting and all that other stuff because, again, I am of the opinion that I believe in the democratic process. Actually, no, it's not even a democratic process. It's more of a democratic republic process. But I believe in that process, so spare me conspiracy theories like my father-in-law. I'm just saying. Think of all the stereotypes of father-in-law. Think of all the stereotypes from TV about father-in-laws. That's mine. But anyway, I digress. Let's talk about the lesson that we're going to do. Actually, no, before I talk about the lesson, let me just talk very briefly about next week. Next week, if we're still alive, we will be back in this room on Tuesday, Thursday for the B week, or that's for an A week, I'm sorry. And we will all be together. And as I counted before, there's going to be about 17 of us. How many are here? 6. There's 7 of you, so think of like 10 more students. And we're going to have those wonderful desk guards. That's going to be fun. Oh, my gosh. Oh, goodness. I honestly don't know what's going to happen, but, you know, I've heard a lot of rumors. I've heard rumors of next week. I've heard rumors at the end of the month. I've heard rumors about staying out until the end of January. I don't know what's going to happen. I really don't. I'm not going to predict what's going to happen because I'm not, I don't know. But anyway, yeah, this is the end of the first marking period this week. I'm still in the middle of grading the majors that you turned in, so they will be put in soonish. Grades are going to be due for teachers by the 18th. So, but if there's anything that you need to discuss with me in terms of your grade, make sure you are emailing me and we will talk about that because today is the end of that marking period. There we go. Haha, we made it. You want to know something funny though? It's the end of the marking period. You know what that means? 25% of your school year is done. Think about that. Isn't that messed up? Just saying. All right, let's talk about stat. I want you to think about what athletic ability is needed to perform the long jump. The long jump is that event where they run, and then they get to a spot, and then they jump, and then they land, and then you measure the distance that they jumped. What athletic attributes would be good to perform well in the long jump? You tell me. No?
Strong legs, I'd say pretty light.
Fast. Got to have strong legs. And you said light. I'm going to say lean. Because light, like, you know, I mean, my son is light. But there's no way. I would say lean. Like, you got to have a lot of muscle, but it can't be like bulky muscle. It's got to be like very lean. You said like strong legs, like explosive kind of like jumping ability or some junk like that. And then when you drift through the air, you kind of do like bicycle kicks and then you land. Yeah. You guys know who Bob Beamon is? Bob Beamon? Yeah. Long story short, Bob Beamon was an Olympic long jumper in the 1968 Olympics. And at that time in 1968, the long jump was only being, the world record was only being broken by like a quarter of an inch, a half an inch, stuff like that. Bob Beamon goes into the 1968 Olympics. He sees the world record is at like 27 and a half, give or take, 27 and a half feet. And he's like, I not only can break that world record, but I'm not just going to break it by a half an inch. I'm going to break 28 feet. I'm going to break it by more than 6 inches. And so he does his jump, and it takes the officials at the Olympics about 20 minutes to confirm exactly how far his jump was because they just felt like they needed to do that. So they posted the results. Bob Beamon, yes, he broke the world record. Yes, he broke 28 feet. He broke 29 feet. And to break a world record like that in that much of a distance comparatively to everything else is absolutely insane. You don't know the name Bob Beamon? Bob Beamon broke the record in 1968. It's still the second longest long jump of all time. Boom. What about the shot put? What do you need in order to perform the shot put? Now, the shot put, just for the sake of argument, you get like I actually looked it up. For guys, it's a 16-pound like stone ball, whatever. And you just, that's the noise they make when they throw it. And they measure the distance that the ball was thrown. What do you need in terms of an athletic ability or attribute in order to perform well in the shot put? Arm strength, little chicken legs. No, probably not chicken legs, but like probably more like upper body, right? Probably more upper body, a little bit more bulkier. I don't know about the chicken legs, but it's like, maybe you get, I don't know. I don't really know. If I had in this room right now an Olympic long jumper and an Olympic shot putter, could you tell me who the better athlete was? You're shaking your heads. No, why? Sure. But they're both like athletes, though, or they're really good. They're both in the Olympics. Who's the better one? You ever hear the phrase comparing apples and oranges? Yeah, you can't compare apples and oranges because oranges suck. Facts. You can compare apples and apples. Stupid game, but you can compare apples and apples, like, a Granny Smith apple versus like a Gala apple, because they're both apples. But to compare an orange to an apple doesn't really make much sense. You can compare an Olympic long jumper to another Olympic long jumper. You can compare an Olympic shot putter to another Olympic shot putter, but to compare them head to head is a little difficult unless you have a way to convert them, to convert their scores, to convert their distances. You can't really directly compare a kilometer to a mile until you convert one into the other. You cannot compare an inch to a centimeter until you convert one into the other. Now, I'm not saying that we convert long jumping distances into shot putting distances, but I'm saying that there is a universal standard of measurement in statistics that we can use to directly compare the long jumper to the shot putter. We can absolutely do that. And we can say we would have evidence to suggest who the better athlete would actually be. Just saying. Apples to apples is a dumb game. It's a better game? Apples to apples with pictures. You ever play that? It's so much fun. My son plays it. Anyway, I'm going to need those notebooks out and open. What in the world? Whatever. Boom. There we go. You guys ever watch this cartoon show called Bluey? No? Anyone have Disney Plus? No? What world are you living in? Gosh. Hulu's dumb. No, but Bluey is a cartoon show it's an Australian show. And it's the best kids show I've ever seen in my entire life. It is the best children's program I've ever seen in my entire life. I was sending my wife clips from the new season just for funsies. Okay. Let's call this normal distribution, because that's where we're headed. And today is the 12th. Make sure I get a marker that works a little better. This one should do it. We'll see. Okay. I have two athletes. Athlete A and athlete B. One of them is good at the long jump, and one of them is good at the shot put. and we are going to compare them to determine who is the better athlete. So in the long jump, athlete A jumped a distance of 6.78 meters. They're at a competition. Athlete A jumped the distance of 6.78, good for athlete A. Athlete B is the next competitor to go. And athlete B jumps a distance of 6.30 meters. Good for athlete B. They're both competing in the same events. Clearly, athlete A is the better long jumper amongst the two. Clearly. Assuming that these distances are typical for athlete A and athlete B. What about the shot put? In the shot put, athlete A threw a distance of 14.77 meters. Now, at this point, I had even said before that one of them was good at the long jump and one of them was good at the shot put. So clearly, athlete A is better at the long jump. So athlete B's got to be better at the shot put. Yeah, athlete B is better. Athlete B threw a distance of 16.40 meters. Kind of move that over a little. There's a glare for the people online. Do apologize for the glare. It's going to be even worse when I put the divider in front of the Chromebook. Just like right there. It's got to be safe. Anyway, who's the better athlete? You pick athlete B for what reason?
Even though the long jump he didn't do as well, right? Typically, right? It seems like it's kind of similar.
Seems pretty close. Question. Not question, more of a statement than a question. I used to compete in Rubik's Cube speed solving competitions. Are you surprised? No, you shouldn't be. Now, I average roughly 14 seconds. In order to qualify for the finals, in order to qualify among the best of the day, I would have to average about 10 seconds. 10 seconds versus 14 seconds doesn't seem like that much, does it? Doesn't seem like that much. But in the world of Rubik's Cube speed solving, 4 seconds is like a mile. It depends on how close the other competitors are. For example, this distance right here, even though it is smaller, you're absolutely right, even though this distance is smaller than this distance, who's to say that this distance might be like an Olympic record versus this distance maybe just being average? I don't know. We don't know yet. We don't know anything just yet. But again, comparing apples and oranges. Comparing apples and oranges. For example, what color would you typically say an orange is? There, you got it. Good job, everyone. You did it. Great, great. But you would expect oranges to all be kind of close together in color, right? What about apples? Yeah. Whole array. That's much more spread out. Comparing apples and oranges. Ooh, goodness. We don't have enough information. You cannot definitively say who is the better athlete because you don't have enough information. You don't know if these are typical shot putting distances or if these are typical long jumping distances, whether these are above or below average. We need more information. So what we need is this. We need to know, well, what did everyone else average for the day? What did everyone else in that particular competition average for the day? And in this case, I'm going to write up an X bar. X bar is your sample mean. The mean of everybody in that competition on that particular day. And on average, on that particular day, The average long jump was 6.16. That was average. Clearly, both of them are above average. The average shot put was 13.29 meters. Clearly, they are above average. Just saying, clearly they're above average. All right, Mr. Geddes keeps walking by, and he keeps looking in my classroom like he's trying to intimidate me, like he didn't win the baseball championship, because he didn't. Sorry, we play fantasy baseball together. Shut up. There we go. I'm also going to need another piece of information. I'm also going to need standard deviation. Why? You'll see. Standard deviation, as a reminder, because I haven't seen you in like 2 weeks, standard deviation is similar to average deviation from the mean. Standard deviation can tell you how varied your data is. It can tell you whether or not your data is much more spread out. It can tell you whether or not your data is much more close together or consistent. The standard deviation of the long jump was 0.23 meters, meaning on average, people deviated from the mean by about 0.23 meters. Some people were below average, some people were above average. Clearly, both of our athletes were above average. For the shot put, the standard deviation was 1.24. Now the plot thickens. Now the plot thickens. Because of the standard deviations. In the long jump, the distances were much more closer together. The distances in the long jump were much more consistent with each other. They were a bit more bunched. Whereas in the shot put, the standard deviation was clearly more, over 1 meter more clearly, but that just means that the shot put distances were much more spread out, a bit more sporadic. So, I'm going to ask this rhetorically. I'm going to ask this not expecting an answer. Don't answer it. Just answer it in your own heads. Who is the better athlete? Again, don't say it out loud. Who is the better athlete? I need to give you a definition. And the definition is going to lead directly to answering that question, who is the better athlete? I talked about a standardized ruler. You know why they call it a foot? Why do they call it a foot? The distance of a foot. Back in the day, when there was a king, they would measure the distance of a foot by the literal length of the king's foot. And then every time they got a new king, they had to remeasure feet in order to figure out that standard. Until they realized, maybe we should keep it the same. Okay. And they kept it the same. There is a standardized ruler in statistics. It's called a z-score. It's called a z-score. By the way, whenever I write the z, I'm always going to put that little line through it just so you don't think it's a 2. A z-score is a standardized measurement for data. It's a standardized measurement for data. It tells you how many standard deviations, and I'm abbreviating, it tells you how many standard deviations away from the mean a point is. It is a standardized measurement for data. It tells you how many standard deviations away from the mean a point is. So if I was going to calculate a z-score, it would be calculated in the following way. The data point minus the average divided by the standard deviation. That is how one calculates a z-score. Now keep in mind, this is if you have sample data. If you have sample statistics, you would be looking at X bar and S. But if you had population parameters, you would be using the following calculation, which is exactly the same. It just has different symbols behind it. So, where does this lead us? We're going to use this formula in order to determine the z-scores for athlete A and athlete B, so we can definitively say who is the better athlete. Let's talk about athlete A. Athlete A in the long jump would have their z-score calculated like this. The data point minus the mean divided by the standard deviation. Yeah, we did it. I've already done the calculation for you. But I wanted to show you something in the graphing calculator real quick, because I don't want you to mess up. Okay. In terms of a z-score, look at these two calculations. Which one is correct? Yes, why? Well, more specifically around the top of the fraction. I can put parentheses all over the place. It may not help. Like, look, I included parentheses. Just because there's parentheses does make a difference, but just because there's parentheses around the numerator makes all the difference in the world. The top one, yes, as you said, is correct. I'm going to round it to 2.70. Now, what that means for athlete A is 2.7 standard deviations better than the mean. Athlete A is 2.7 standard deviations better than the mean. Good for them. Now, there are certain standard deviations that we can be that people would consider to be like, oh, that's really good. If you're 2.7 standard deviations away from the mean, then you are actually considered what is known as an unusual data point. And I'm going to give you that definition written down later. Anything more than 2 standard deviations away from the mean, either above or below, would be considered unusual. Now, just because you're below the mean doesn't necessarily mean a bad thing. Because think about like the 100-meter dash, for example. If you're competing in the 100-meter dash, you want your time to be lower than the mean, so you would want a z-score down there. But in the long jump, distance matters, so 2.7 is where we're at. Somebody had an amazing statement last year where they said, Mr. Markey, my goal in life, I want to be 3 standard deviations above the mean. I'm like, really? They're like, yeah. I'm like, okay, if you're 3 standard deviations above the mean, that is remarkable in whatever the heck it is that you're talking about. Being 3 standard deviations above the mean is like, if it's the long jump, you're talking like Olympic level. I know. If it's debt, never mind. 14.77 minus 13.29 divided by 1.24. This is the shot put calculation for athlete A. Athlete A threw a distance of 14.77. There's the average, 13.29. There's the standard deviation, 1.24. It calculates out to be 1.19. All right. I have a little bit of a reveal in a little bit, but I'm going to save that reveal. Let's talk about athlete B. Now, like I said, I've already done these calculations for you, just to save a little time. But notice in the calculation, for the long jump for athlete B, every number stays exactly the same. The mean, the standard deviation. The only thing that changes is obviously the data point that belongs to athlete B. Now, athlete B was better than average. However, athlete B was only about 0.61 standard deviations better than the mean. And in the shot put, which seemingly athlete B blew the competition away, athlete B threw a distance of 2.51. Now, there's a few things that we can do at this moment, which I'm going to share with you. Well, let's compare the two. Athlete A is the better long jumper. Athlete B is the better shot putter. In the events that they are better at, athlete A definitely outperformed the rest of the field better than athlete B did. Athlete A performed better in the long jump by 2-point standard deviations. Athlete B competed better in the shot put only by about 2.51. Then, when you compare the events that are not their best event, athlete A is not as good in the shot put, but was better than average by about 1.19 standard deviations above the mean. Whereas athlete B, although better than average, was not as better than the field in comparison. You have to be able to compare them to an average and a standard deviation. Then you can consider it to be a z-score. Now, here's the thing. We cannot directly compare long jump to shot put. We can't directly compare it until we convert it. Once we convert it into z-scores, which again, these are standard deviations above or below the mean, that's the unit that is on that number. It's technically 2.7 standard deviations above the mean or below the mean, whatever it is. That's what a z-score actually is. You don't actually write the unit on there, but that's what it is. And it's the same exact type of unit as 1.19, as 0.61, as 2.51. And because now that we've converted them, we could do something like this. Oh. I can say that the total combined z-score for athlete A is 3.89. And I can say that the total combined z-score for athlete B is 3.12. And now I have straight up evidence. Evidence to suggest that athlete A is the better athlete. I mean, if these numbers were a bit closer together, like if it was like 3.12 and 3.13, that's a bit harder to argue. But these numbers are far enough. Conclusion, athlete A better. That's my general conclusion down there. My silly example. Now, in order to visualize this, because these are just numbers sitting on a page, in order to visualize what is better, what is extraordinary, and what we would expect to be average, we need to look at a normal curve. Now, before we left for this week off, I introduced this very slowly, but now we're going to have to deep dive it a little more. So I'm going to have to draw. That's a terrible normal curve. That's terrible. I'm going to draw that again. All right, you ready? You ready for this? It's going to make it all the way across. You ready? This is going to make it straight into the garbage can. You ready? Nailed it. Let the record show, for those who are not in the classroom, I totally threw that ball of paper across a distance and it made it directly into the garbage can. Am I lying? No. Anyway, there's a better normal curve. I mean, it's slightly better. It's not great, but whatever. You know my favorite thing about telling jokes? It's when they're funny, but they're not funny enough, and I end up getting people to just breathe slightly out their nose. I don't know. Why did they let me do this job for free? Anyway, right in the middle, there's your mean. Your mean is 6.16 because I want to create a normal curve for the long jump. Now, up the ways a little bit, right at that point of inflection, I get 6.39 meters. Mr. Markey, 6.39? Where the heck did you get 6.39 from? I got it by taking the average and adding one standard deviation. The standard deviation was what for the long jump? 0.23. I added 0.23. That's all I did. I'm going to do it again, but I'm going to do it over here. 6.62. I'm going to do it again. I'm going to do it over here. 6.85. Now, these numbers represent the distance in the long jump that is 1, 2, and 3 standard deviations above the mean. Because these things are symmetric, I can do the same thing to the other side by subtracting 0.23. 5.93, 5.70, 5.47. I would argue that basically every single athlete at this particular competition fits somewhere on this curve. I would argue that every single athlete at this competition fits somewhere on this curve, and it has to do with the empirical rule, which I'm going to remind you of in a minute. If you are someone at this competition who jumped farther than 6.85 or fewer than 5.47, then you are extremely out of the ordinary. If you jumped farther than 6.85, perhaps you belong at the Olympics. If you jumped shorter than 5.47, perhaps you should not have been competing in the first place. But almost all of the real athletes at this competition fall somewhere on this curve. In fact, according to the empirical rule, and I wrote this last time, I'm going to do it again because it's always good to draw and label your graph. 68% of the data points fall within one standard deviation away from the mean. Plus one standard deviation, minus one standard deviation, 68% fall within that range. %95 fall within that range. -2 to +2 standard deviations away from the mean. As I said, this is the empirical rule. Now, typically, if you ever see these kinds of things drawn out on paper, a lot of the time they will never have room in the curve to do the third one. But if you're going to go -3 to +3 standard deviations away from the mean, you would have captured 99.7% of all data points. Now I got to look it up. What was Bob Beeman's distance not in feet? I want to know what it was in meters. Bob Beeman, there he is. Bob Beeman. There it is. Look, he broke the existing world record by 21 inches, almost 2 feet. That's insane. It is still the Olympic record and the second longest wind legal jump in history. What was the distance? There it is, 8.9. 8.9. Go back to this. if you're at 8.9 meters, clearly you are the best of the best of the best. 8.9 meters, according to what I just read, only one person in human history has ever jumped farther than that. So you would be all the way down there. But everyone else would kind of be within our range here. I'm going to draw on the thing. Now, here's the thing. I'm going to draw directly on the board. Where's my red marker? I'm going to draw directly on the board. Oh, wait, it's in my pocket. I got it. How far did athlete A jump in the long jump? Athlete A? 6.78. So right about, there's athlete A. Athlete A was more than 2 standard deviations above the mean. Now remember, this curve is similar to what we would get with a histogram. A histogram would be a representation of all the data points plotted. And the higher the bar, the more people kind of were in that range. You can see athlete A all the way down here. Not as many people jumped that distance. What about athlete B? How long did they jump? How far did they jump? 6.3. So under here, there's athlete B. You can see that athlete B, many more people jumped around that distance that athlete B jumped. Better than average, yes. But compared to athlete A is like an unusual data point. Kind of in a league of their own. That's strange. Now, one could argue, okay, check this out. Athlete B jumped between 0 standard deviations and 1 standard deviation. Athlete B jumped in this range right here. Can you tell me what percent of long jumpers also jumped in that range? What percent of long jumpers also jumped in that shaded region? 34. Because if -1 to +1 standard deviation away from the mean is 68%, then half of that, because it's symmetric, half of that is 34%. Yeah. So in that little range that athlete B jumped, 34% of data points fell. So, I mean, that's very common. That's very common for athlete B. Oh no, my marker. Let's talk about athlete A. Now, athlete A, I'm going to go a little bit farther here. Check this out. I'm not only going to fill in that, but I'm going to fill in all the way down to the end. All of that. I ask you, in that shaded region, that athlete A falls. Athlete A, clearly the superior long jumper. What percent of data points fall within that little shaded region? Ooh. I think he's got it, but I'm waiting to see if anyone else is going to jump at it. Yeah? No, not 1.35. 2.35. You're getting closer. Where are you getting these numbers from?
I subtracted the 99.7 from the 95 to get like the outside numbers.
Ah.
And then I divided that. And I mean, in my head, so I don't know.
Okay. What are you going to say?
You're going off the graph, so I just say the rest of it, 2.5.
It's exactly 2.5. Yeah. According to the empirical rule. Mind you, because the empirical rule is not accurate. The empirical rule is just an estimation. The reason why that is, I saw what you were doing with the 99.7, but check this out. 95% fall in the middle. 95% of all data points fall between the two lines that I just drew. Meaning 5% fall outside that range. And because 5% fall outside that range, and because it's symmetric, 2.5% would fall here. Again, I'm including all the data points off to the end of infinity, all the way to Bob Beeman and whoever beat him. It's a really weird thing. Again, this is according to the empirical rule. This is according to the empirical rule. What about right here? What about right there? Between 1 and 2 standard deviations above the mean. This one takes probably a little extra finessing. Not that hard, though. It's not that hard to figure out, according to the empirical rule, exactly what percent of data points fall within that shaded region. What are you thinking? Let him think. Let him think. Let them think. You got your brother in an earpiece, don't you? Yeah.
He's got all his notes from.
Yeah, of course he does. That's all he's doing with his time now. He's live streaming in to my lessons to give you answers. All right, what do you got?
13.5.
Yeah, it's 13.5. It's 13.5 because, again, if you're looking at this range between -2 and +2 standard deviations away from the mean, that encompasses 95% of the data. Now, if you subtract the 68% that's in the middle, you get 27, which is split up between this region and this region. And because it's split up evenly, you just got to divide it by 2, 13.5% of the data. Again, that's according to the empirical rule. That's according to the empirical rule. Now, you might see it written as the empirical rule. You may see it written as something else. But typically, they'll refer to it either as the 68, 95, 99.7 rule, also known as the empirical rule. Now, keep in mind that is just an estimation. It's just an estimation. It's not 100% accurate, and I'm actually going to show you that it's not 100% accurate. It's all that we had to go on. Think about it. When were graphing calculators really introduced to the general public? Do you know when? The 90s, the 1990s. Statistics has been around for 400 or 500 years. They weren't able to calculate the exact values of these things until the last century. So we had to rely on something a bit more rudimentary. And the rudimentariness of it all is the empirical rule. Now, the fun thing is, if you're going to be doing problems on the AP statistics test, they're actually okay with you using the empirical rule. They're actually okay with it. You just have to justify what you're doing. A few bullet points that I need to give you before I show you something on my calculator, because I want to show you how to do some calculations in a little bit. First of all, if you have a normal distribution, I'm going to abbreviate, then you must think in z-scores. Not to bring up PTSD, but you all remember geometry, right? Okay. Some of you said that with disdain in your eyes. But I asked yesterday's class, they didn't know, and I still don't know because I didn't bother to look it up. What is it called in geometry when you have an if-then statement, but you reverse the statements and they're still true? They couldn't tell me yesterday. None of them remembered. And here's the thing. Even if you know the right answer, I can't tell you if you're correct because I don't know. I don't know. But you know what I'm saying, though? Like, if this, then this, but if I reverse it, it's still true. Well, that's what's happening here. If you have a normal distribution, then you must be thinking in z-scores. If you're given z-scores, then you must be thinking a normal distribution. They go hand in hand with each other. Z-scores are linked directly with your distribution being normal. Normally shaped, a bell curve. More than 2 standard deviations away from the mean is considered, quote, unusual, end quote. more than 2 standard deviations away from the mean is considered unusual. Now, somebody had an amazing question for me yesterday, and I figured instead of like waiting for someone to ask it, I'm just going to say it anyway. Well, what they said was, Mr. Markey, is this definition similar to that of outliers? And I said, ooh, good question. No. Even though they're in the same vein of things being above or below the mean, if you're going to consider something to being an outlier has to fit this definition, meaning that the data point is outside that range. If it's an outlier, it's outside the range that I just wrote on the board, that formula. But if you were going to designate something as a data point that is, quote, unusual, then by definition, it's more than 2 standard deviations away from the mean, either 2 above the mean or 2 below the mean. Yes, they're kind of linked, but if you're given that verbiage of unusual, I need you to be thinking this definition. If you're given the verbiage of it being an outlier, I need you to think this definition. So we need to keep those straight in our mind. A little weird, I know, but meh. Go away, outlier. I actually did the calculation. Derek is an outlier. Derek, according to most recent data for average adult male height and standard deviation, is approximately 2.5 standard deviations above the mean. Approximately 2.5. Me, I'm below the mean, clearly, but I'm pretty close to average, so I'm kind of typical. I'm within that middle 68%, whereas Derek is just tall. Now check this out. Fluffy language. As long as your data is, quote, nearly normal, end quote, then using z-scores is appropriate. Again, z-scores are intrinsically linked to a normal distribution. But if you have a set of data and you look at the histogram, and the histogram, it could be normal. It's not quite there, but it's kind of close. That's good enough. It fits the condition. This is a really weird kind of way of putting it. Like, as long as it's like close enough, yeah. As long as it's close enough, we're good. Then you can use z-scores. Yeah. You guys ever do like a linear regression, line of best fit stuff? Cool. There's a condition in that chapter that we're going to get to where it's like, okay, look at the scatter plot. Does the data look straight enough? If it does, then we're good. It's like, what? That's a ridiculous statement. I know. But even in their assumptions and conditions, statisticians still use fluffy language because they know that the data is never going to be perfect. They know that the data is not going to be perfectly normal or perfectly straight or something like that. They know that. And because of that, they have to include that little fluffy wiggle room. As long as it's close enough, then we're good. Oh, statisticians. Now, we're talking about the election before, talking about a margin of error. Now, a margin of error would be something like this, because we're eventually going to get to this chapter in the future. But like a margin of error is like, okay, I'm predicting 51% with a margin of error of 3. That means, okay, 48 to 54. That means that I believe with some confidence that the true percentage is going to be within that range. But I'm only like 95% confident. You can never be 100%. You can never be 100%. Which means 95% of all similar constructed intervals would capture the true proportion. I'm just simply hoping that I'm one of them. Again, that's a definition for the future. Okay. I want to show you something on my phone, because, wow, I have 13 text messages. What is going on? Sorry, just, what the heck, dude? Anyway, back to this. Check this out. On your Chromebooks, which I'm not expecting you to open the Chromebooks now. I don't really want you to right now. I'd like you to look what we got right here. And I'm going to compare it against what I got on my 83 as well. Okay. Reset. There we go. Oh, no. Reset. There we go. There is a function called distribution. I don't know if you can see it that well. There's a button here that says VARS, V-A-R-S, and above it written in yellow where I'm pointing, it says distribution, although it's kind of abbreviated. On the 84s, you have the same button, VARS, but it's written in blue. If you hit second VARS, it'll take you to this screen. Now, on this screen, you are going to be spending a good deal of time of this school year on this screen. Because, yes, we are going to use that normal function. We're going to use that inverse norm function. We're going to use that T function. We're going to be using this geomet and binom function. Hey, do you know how to pronounce that P word? Anyone taking French? No? Poisson. Yeah, it's poisson. French is a dumb language. I tell Madame Morris that every day. No. She gets so mad at me. I'm not going to be interested in the normal PDF. I'm actually just going to be interested in the normal CDF. PDF is probability density function or probability distribution function, depending on who you talk to. But CDF is the one that I am interested in. That is the cumulative density function. I'm also going to show you how to use this inverse norm in a moment as well. I'm going to show you how to do both. Now, if you're using the calculator on the computers, when you go to normal CDF, you'll come to this screen. Whereas, if you're using the regular 83 calculator and you go to normal CDF, you go to this screen. I need you to see what both of them do. On the 84, it has lower, upper, mu, and sigma. Now, here's the thing. If you have a normal distribution with a mean of 0 and a standard deviation of 1, then basically each of these data points, they just represent z-scores. That's all they do. If you keep the mean at 0 and the standard deviation at 1, then it's going to assume that your lower and upper limits are z-scores. Please keep that in mind. Now, if I were going to go -1 to +1 standard deviation above or below the mean, -1 to +1 z-score, according to the empirical rule, what percent of the data fall between -1 and +1 z-score? 68. Now that's an approximation. This is the exact number. Now, if you do it on the Chromebook, you'll have to hit paste, and then you'll have to hit enter, and clearly it gets you the same thing. Yay. I can do it again with 2. Watch this, with 2. See if I do that here. 2, 2, boom, boom. Get rid of that plus, boom. 95%. I'll only do it here for this one, but then you get 99.7%. Hey, what was that thing where we got 13.5? Do you remember what z-scores they were where we got 13.5%? 1 and 2? Check this out. 13.5%, approximately. Yeah, obviously it's like 13.6 really, but you can either use the empirical rule or you can use the exact value on the calculator. But here's the thing. If I go normal CDF, there is a way to type in mean standard deviation. 6.16.23. That is the mean and standard deviation. Now, if I go back to this normal curve that I got right here, this one that we drew right here, this weird one, between, you said 13.5% was between 1 and 2 standard deviations. So that's 6.39 and 6.62. 6.39 and 6.62. If you actually type in the mean and standard deviation, which if you were to do it on the Chromebook, it would look like that. If you were to do it on an 83, you would actually have to type this whole thing in with commas in between each of the terms, in that order: lower limit, upper limit, mean, standard deviation. And you can see that 13.5% right there approximately. It's kind of nice. If you don't put in a mean and standard deviation, then the calculator is going to assume that you are dealing with z-scores. But if you put in the mean and standard deviation, then your lower and upper limit have to be data points from the context of the problem. So let's write down some of this stuff, because I want to make sure that you at least have this, and then we'll have practice with it another time. Here we go. First of all, normal CDF, lower limit, upper limit. It gives the percent of data points between two z-scores. It gives the percent of data points between two z-scores. Now, technically, like I said, you could use the empirical rule, but the empirical rule only really helps you if the z-score that you're dealing with is a whole number. A whole number. If the z-score that you're dealing with is a fraction of a number, then perhaps you need to go to normal CDF. But you could also do this lower, upper, mu, sigma, where you actually get in the mean and standard deviation. And it gives the percent of data points between two data points. It's kind of nice. Now, just for the sake of argument, let me tell you what inverse norm does, and then I'll go back to the calculator with the time that I have left. Now, normal CDF gives you the percent of data points between 2 points. Inverse norm, and I'll show you what you're actually going to type in a moment. It gives you the data point at that percentile. It gives you the data point at that percentile. So inverse norm, it kind of does the opposite. Normal CDF gives you the percentage of data points between 2 points, whereas inverse norm gives you the data point at that percentile. So what you would have to do for inverse norm is you would have to type in percentile, and then it's optional whether or not you do mu and sigma. If you don't type in mu and sigma, it'll give you a z-score. If you type in mu and sigma, it'll give you the data point in the context of the problem, which is kind of nice. I'm going to show you what that looks like in a moment. I'm going to show you what that looks like. Let me see here. I'm going to zoom in. Zoom. So for example, inverse norm, if I just typed in something like 0.84, it would give me the z-score at the 84th percentile. which is nice. That's a z-score at the 84th percentile. But if I typed in a mu and a sigma, it would actually give me the data point at the 84th percentile. We'll pick up with this more next week. I see you on Tuesday. Y'all leave. Anyway, we'll pick up with more of this on Tuesday. We'll get a lot more practice. No worries.